All right, so in this example, we are going to find the magnitude of and direction of the magnetic field above a finite wire. So let's draw our finite wire. And let's say that this has a length of 2 times L. We're going to go from minus L to plus L. So this is our midpoint here, and that's going to be the x-coordinate of our point of interest. We're going to make it some height y above the midpoint, and we're just going to pick a point over here to define our little piece of the current, dl. Our current is flowing from left to right, and that, of course, sets up where the x-coordinate is. And let's draw our vectors. So here's our r vector. Here's a little unit vector, r hat. And we can also use x and y and r to define theta. Okay, so what is the B of R law tell us? Well, we know that B of R law can be written as the integral of dB, which is mu naught I, all constants, over 4 pi times the integral of dl crossed into r hat all over r squared. And what we're going to see in this example is that r actually changes as we do the integral, unlike the last one with the ring. So we're going to have to leave that on the right-hand side of our integral. Okay, so let's look at this first term, the cross product term. So dl crossed into r hat. Let's calculate its magnitude. Well, its magnitude is going to be the magnitude of dl. Magnitude of r hat, by definition, is 1 times the sine of theta, the sine of the angle between those two. And that, if you do the right-hand rule, dl pointing from left to right, and r hat there, which is going to change, but you can do this cross product with the right-hand rule. That is going to point into the page. Let's go, excuse me, out of the page. Sorry about that. And the easiest way to check that would be at the actual midpoint, dl pointing here, and this is also a result of symmetry, but dl would be pointing from left to right, r hat in this case would be pointing straight up, and your thumb would be pointing at you. So out of the page. Okay, now we can set up our integral, and we're going to start off just looking at the magnitude, because we now know the direction. Magnitude is going to be dB mu naught I over 4 pi. We're going to integrate from minus L to L. This is going to be dl sine of theta over r squared. And we know a few things about r and the sine term. The sine term is opposite over the hypotenuse, so that's going to be y over r squared. We're going to combine those terms in just a second. This r changes as we do the integral, and we're going to sub in for that term now. So that's going to be x squared plus y squared. When we combine this term and these two underneath, that's going to give us cubed. So this is going to be 3/2. And we can factor y outside because that is not going to change with time, right? Because we're integrating essentially in the x direction. So this y can get moved outside. 4 pi sits underneath. And we're going to go from minus L to plus L. And now we can say dl is equal to dx because we're purely in the x direction. This is going to be x squared plus y squared. I don't know why I wrote it like that. Cubed. Okay, so this is a integral that we can look up. Look this one up. And when we do that, we find the following in our integral table or Google or wherever else you want to look for that integral. Here's the term that was sitting outside. And this integral evaluates to x over y squared times the square root x squared plus y squared. And we are going to evaluate this at x minus L and x of plus L. All right, so there is a cancellation of the y terms. We can bring that y squared out front. That's not going to change anything, so this would be a 4 pi y squared, and this term would cancel out. And what's left? Well, we have a x, so our plus L. This is going to be L squared plus y squared minus a negative L over negative L squared, which is just L squared plus y squared. And so these two become positive, and we have a nice little sum of mu naught I times 2L over 4 pi y times square root L squared plus y squared. And what cancels? Well, we get a 2 canceling out. And that leaves us with a mu naught I over 2 pi y. And this is an L over square root L squared plus y squared. And from what we talked about before, that is going to be out of the page. So this is our magnetic field. Now, one of the things that we should consider with this is what happens when we get to an infinite wire, right? So let's just explore this a little bit. As L goes to infinity, what does this look like? Well, that term, this term over here, as L gets really, really large, the limit of that is essentially going to be 1. Right? L is getting really big, and we have a very big number squared, and then the square root. And so those two limits are going to trend towards 1. So let's just be explicit about this. L squared plus y squared trends towards 1. And so for an infinite wire, we get the following. Just that term out front. mu naught I over 2 pi times y, where y is our separation away from that infinite wire. And we're going to see that show up again later in the chapter.